Our final speaker will be Shahin Nasr, speaking about amblyopia impacts on activity within human V2, V3, thick and thin stripes during binocular summation.
Yeah, the last speaker, so you survived. So thanks a lot, everyone, and thanks for attending this talk. I'm going to talk about impacts of amblyopia on the function of V2, V3, thin and thick stripes during binocular summation. So, and I have no relationship to disclose. So I think we all know that what is binocular summation. It's not a new phenomenon. Technically, it refers to improved visual performance when we do the task binocularly rather than monocularly. And is binocular summation affected by amblyopia? Yes. And for many, many years, we have known this effect. And for example, when you look at, this study by Parton and Gilchrist, they have shown that in amblyopic individuals, usually, the performance is improved when we do binocularly compared to when we do the task, based on the good eye or amblyopic eye. But when it comes to high spatial frequency components, it's not happening. And technically here, performance is better when you do that based on the good eye. I use the term that they used, compared to when you do the task binocularly. I think to some extent it's also related to our first talk by Dr. Birch, and but we can talk about that later. Based on this, subject and many other that participated in their study, they suggested this: that binocular summation decreased as the difference between the two eyes increased, and further increases in the monocular difference produce binocular inhibition. This is what they call binocular inhibition. It means that the performance based on binocular condition is worse than when subject did the same task based on good eye. Also, based on the questions that Dr. Birch received, and also if you do a quick literature search, you will find that our knowledge of this phenomenon in neuronal level is very, very limited, and especially in human, technically very close to zero. This is focus of our study. We want to know what is happening in neuronal level, and we have studied spatial frequency encoding and binocular summation in human extrastriate cortex in mesoscale level. Every subject was alive, and there is no blood on my hands. So it's important, and I emphasize on using mesoscale levels, because previous studies have already shown that. This is a data based on monkeys by Roger in 1983. We have shown more or less the same data in 2016 and 2017. And that data suggests that when you look at the area of V2 and also V3, you will find a lot of small neuronal clusters. For example, thin and thick stripes in V2 and their extension toward area V3. And these clusters, their spatial frequency preference differs significantly from each other. So there is a good chance that they are affected by amblyopia differently. This is what we want to test here, especially during binocular summation. So our approach was first localize V2, V3, then localize thin and thick stripes within them, and then measure and examine their response to monocularly and binocularly presented stimuli. 11 amblyopic subjects participated in this study. 5 of them were strabismic, 4 were anisometropic, and 2 of them showed mixed cases. Best corrected visual acuity was 20/40 to 20/300. 6 out of 11 showed stereo blindness, and 10 out of 11 showed suppression of one eye, and the other subjects showed diplopia. And we used high-resolution fMRI collected in a 7T scanner, and the spatial resolution that we had was 1 millimeter isotropic. These are the stimuli that we presented. Luminance variant gratings, and the spatial frequency varied between 0.1 cycle per degree to 5.79 cycle per degree. They were either high contrast or relatively low contrast. You can say that, very low contrast. And it was block design. It means that the spatial frequency and contrast only varied between blocks, and each block was present for 16 seconds. Task was completely orthogonal to the stimuli that we used. They were color change detection for the fixation spot, and it was completely irrelevant to a spatial frequency of a stimuli. And if you're interested in details of the task and the stimuli further, and also details of scan parameters, you can read this paper. And regions of interest, as I told you, thin and thick stripes. Thin stripes, they were localized based on their color selectivity, and my apology. And thick stripes were localized based on their motion selectivity. This is the example of, one amblyopic subject. After close to 4 hours of scanning over, 8 hours of scanning over 4 scan sessions. And to me, it's Mona Lisa, but I'm not sure, how you feel. But, the thing is, when you look at, area V2, you can see these, small, patches with different selectivity. And I will show you the data that shows that a spatial frequency encoding varies between 2. Please pay attention to the scale. This is something like 5 times better than a regular fMRI scan. And to gain something like that, you need to have a 70 scanner. You need to put down something close to $10,000 per subject. So thanks, NIH. And you can see the extension of, this, stripes to area V3, also to some extent to V4, but for some technical reasons, I prefer not to talk about V4 activity. And if you were, interested in, details of that, there's a video of, the method section. There's a preprint of our papers. Please have a look at it. But result. So here you can see the activity collected in color selective stripes, motion selective thick stripes, low contrast, high contrast, and result of a simulation of non-amblyopic eye, amblyopic eye. Each graph you see fMRI activity versus a spatial frequency. And as you can see, in color selective ones, when non-amblyopic eye is simulated, there is a preference for higher spatial frequency components. Same location when it's based on amblyopic eye stimulation, response to high frequency components drops. When you look at motion selective stripes, just don't forget they are interdigitated relative to each other. So the distance between them is something like few millimeters. Here you see a more general effect. Statistically, here you see an interaction between the spatial frequency and a stimulated eye. Here you don't see that interaction. You see effect of a spatial frequency and effect of effect of a stimulated eye, but not interaction between them. When it comes to high contrast, similar to behavior, there is almost no difference between the two eyes. The pattern becomes similar. This is also the same pattern that we see in controls. And this is monocular versus binocular. Don't forget what Parton and Gilchrist, they showed. So here you see almost the same thing. When you look at low contrast, low spatial frequency components, you see that there is an advantage for binocular stimulation compared to non-amblyopic eye stimulation and amblyopic eye stimulation. But when it comes to high frequency component, you see some level of binocular suppression. It's not significant because the level of binocular suppression varies from one subject to another subject. I will show more data later. And then when it comes to motion selective ones, you see almost the same phenomenon. Again, here there is some level of binocular suppression. When it comes to high contrast stimuli, this effect is almost gone. You don't see that much binocular suppression, but binocular summation exists, still is there. And it also means that the reason that you're not seeing the effect here or here is not because of saturation of result, because activity can go much higher, but you don't see it here. So just consider that. And just to, compare the level of, binocular summation and interocular difference as suggested by original behavioral study more directly, here we measure the, binocular summation effect as response to binocular stimulation minus non-amblyoptic eye, and the interocular difference is clear. Response in thin stripe, thick stripes, solid line, dashed line, so you can see it hopefully also there clearly. And all activities, just to avoid, activity to be dominated by good subjects, whatever you call it, everything is normalized relative to response to non-amblyoptic eye stimulation. You can see that the level of binocular summation enhancement is larger for thin stripes compared to thick stripe, while the difference between the two eyes is almost, on average at least, is the same in these two, neuronal clusters. When it comes to neuronal inhibition, you see it here that the level of inhibition is slightly larger in thick stripes compared to thin stripes. When you go to high contrast stimuli, that inhibition is almost gone. The difference between the two eyes is almost gone, but there is still for low contrast stimuli, low special frequency stimuli, you still see that binocular summation effect. However, at least for these stimuli, for activity within thin stripes, you see that now it's 80%, here it was 120%. So just consider that again to clarify, that effect in thin stripes is more dependent on the contrast. So the last result data, so you can see that, when it comes to individual subject level, there is also a correlation. So here there is no normalization. The point is when you show increase in the level of difference between the two eyes, the level of binocular summation effect goes down. There is a negative correlation. This correlation is stronger in color selective ones compared to motion selective ones. In color selective ones, trend remains the same for all the spatial frequencies, not in the motion selective ones. Again, here trend remains the same. For also high contrast, in both conditions, the level of correlation is stronger in color selective versus motion selective ones. So summary and conclusion, response to high spatial frequency, low contrast stimuli is stronger when they are presented to the non-amblyoptic eye rather than the amblyoptic eye. Binocular summation enhances the response to low spatial frequency component, but not high spatial frequency component. And this enhancement, when you compare thin and thick stripes, is stronger in thin compared to thin stripes. And this enhancement shows a stronger negative correlation with the level of interocular difference. So, thanks a lot to my team. Thanks a lot to a wonderful friend and colleague, Dr. Rick Geyer. I really don't know how to thank you for your help in recruitment, consultation, and funding agency. Honestly, I said that, without their help, it's impossible to go even close to a study like this. And last thing, if you're interested in this, if you have subject, and you can, introduce them to us, please, please, please do that. It's really hard to find adult amblyopes that are interested in participating in a study. It's not like, finding children, because you regularly work with them. Adults, you rarely see them. Please introduce them to us. If you are interested in collaboration, drop us a line. We will have a chat. And for younger, audience, if you're looking for a postdoc position, please send me your CV. We will have a chat. Thank you. Podium is yours. You usually have a question, so.
Congratulations.
Thank you.
On finally having, I think, acquired the holy grail of functional imaging in amblyopia studies.
Thank you.
I think back to when I was probably the first functional imaging in MRI with positron tomography in the early 1980s. This is what I always imagined somebody might do. So I am really taken aback at the excellence of this result and how perfectly it correlates with what we understand about binocular summation. You've demonstrated that every feature is evident in this area that you're studying. So, wow.
Thank
But
you.
I have a technical question.
Sure.
How did you keep your subjects from falling asleep during this approximately 2 hours of scanning per session?
I think I said that, they were doing a task, color change detection for the fixation spot. So every few seconds, the color of fixation spot varies and varies from red to blue, blue to red. They have to press a key and, report that. There is no way that you can go to sleep and, do the task. And one thing that, you have to consider, I never, I never feel worried about amblyopes go to sleep because they are such a wonderful people and so motivated to help. We have their performance. We have everything that assures us they are not asleep. Their performance is close to 100%. So that's the thing. But it's usually in human studies not a factor that, in 1 hour, 45 minutes, they go to sleep.
You have excellent subjects because in the days of positron tomography, it took between 2 minutes and about 30 minutes of exposure to the stimulus because the isotopes had various half-lives. And nothing short of a James Bond movie would interest them enough to avoid staying awake. So you must have been rewarding them or motivating them very highly to identify the color changes. I'm very impressed at the quality of what you've done. Congratulations.
I have brothers and sisters, let's say that, I look at them always like that. And sometimes I joke that, and it's joke to them, but to me, I take it seriously. If you have a flat tire on the street, call me, I will come for you.
That's how to do it.
Some great data. I was wondering, since you didn't resolve the intervening pale stripes between each thick and thin stripe, whether you might have some kind of bleed-through or of some of the functionality between the thick and thin, such as a high spatial frequency response, and the so-called thin might actually be due to some from the pale stripes that are next to it.
Okay, so technically, when it comes to pale stripes, it's really hard to localize pale, just pale, because there is no single functional character that you can use to say that this is just pale and it's not thin and thick. Pale usually share one thing with either pale, with either thin or thick. It's really hard to put it aside. Do you want to add something?
Well, one thing you could do is that since the pale stripes are orientation tuned, but the thin stripes are not, that you could identify the non-orientation versus orientation tuned to clearly show what is absolutely thin and what might be pale versus thick.
And I respectfully disagree with that because, there are studies by, for example, Wim van Duffel and Roger Tootell. They show that, even, thick stripe, they show a strong orientation selectivity. And there are also studies by Anna Rowe in monkey optical imaging. Again, they showed that, thick stripes also showed orientation selectivity. So my point is that when you do orientation selectivity test, it's pale stripe plus thick stripe. If you go to other things, it's pale stripe versus, for example, color, pale stripe versus thin stripe. There is nothing that just activates pale stripe and neither were thin and thick. It's a still open. I will be very, very happy to discuss it more with you. Very good point. Let's talk about it.
Okay. Do you think your data says anything about M versus P channels?
Yes, we can say that. So there is a paper right now that we have that thick stripe motion selective are a part of magnocellular stream. And when it comes to color selective ones, they are part of parvocellular stream. In that level, we have a paper published in 2017, but that's for individuals based on normal vision. When it comes to amblyopes, I still don't have any published data. Thank you.
I think we can take only one more question.
I will stay here as long as you are.
Hi, it was a great talk. So,
Thank you.
I may have missed that, but did you show any correlation between your summation factor as obtained from imaging compared to function, for example, discrimination or detection thresholds?
Okay, you're talking about technically the relationship between fMRI and behavior.
Right.
I didn't show that one, it's ongoing. So now the same subjects are doing behavioral tasks, and you know the general effect that Parton and Gilchrist they showed, we can replicate it, but I didn't have a chance to check the correlation between behavior and fMRI. It's still ongoing. Good question.
Okay, great, thanks. Another question, sorry.
Sure, go for it.
Okay.
I'm sorry.
So this is not my question. This is a question that's posed to me by many, many people, and I'm going to pass it on to you. Is there a model for binocular summation in not just normal people, but in disease populations like amblyopia?
What do you mean by model? So the model, you know, if you're, you know, the study by Gilchrist and Parton, they offer the model. They said that there is a relationship between interocular difference and binocular summation. But obviously the concept of is there a model depends on, you know, what's your exact question.
My exact question is, how do you predict binocular summation from a patient that comes into the clinic?
So based on, you know, the level of, you know, acuity difference between the two eyes, you can predict it to some extent, but that's all that I know. That I can, you know, based on modeling, I can, you know, offer that. But
okay, thank you.
You're welcome.
Okay,
Thank
you. I think with that we come to the end of the session. Thank all the speakers one more time. Thank you very much, and thank you for your attention.